welcome back to our series of math videos. Today's topic is on Pythagorean and sum and difference identities. So our outcomes will be to simplify and manipulate expressions containing those trig expressions using the identities, and also using the identities to find exact function values. First off, just a quick little story. When I was in university, I took a class called Math 2450. And at the time, it was my worst class. And I just struggled horribly with it because I couldn't understand how the instructor went from one spot to another spot. It seemed like it was magic what was happening. So I didn't do too well in the course, so I took it again. Okay, I got a D. Took the class again. The next instructor introduced me to this idea of bags of tricks. And what was happening in the first time was the instructor was using too many tricks in a row, and I couldn't see where he was getting them from. And when we're dealing with trigonometric identities, this is a useful thing to remember, is that what we're doing is we're replacing one thing with another thing, and we need to have these sort of bag of tricks at our disposal at any time, or these identities, as we'll see them defined in a second. Currently, these listed on the page here are probably some of the bags of tricks that you have. You know how to use the principle of zero products and addition, subtraction, multiplication, division principles. We saw earlier in trig that sine and cosecant are reciprocal ratios. You've used this to help you with quadratic equations. We've seen this one too as a relationship between adjacent, opposite, and hypotenuse sides. And we've also used these. So you already have a lot of bag of tricks. Today we'll show you some more tricks that you can use in either simplifying expressions, that's what we'll do in this section, and in future videos on solving trig equations. To begin with, what is an identity? An identity, by definition, is an equation that is true for all possible substitutions of the variables. So if I'm dealing with a right triangle, I could say that always x squared plus y squared is going to be r squared all the time. That's an identity. So in an equation, if I saw an r squared, I could replace that with x squared plus y squared. Also, I could manipulate this, and I could maybe move the y squared to the other side and subtract it. And so, anytime I saw an x squared, I could replace it with r squared minus y squared. So this is something that's true for all possible values of x, y, and r in a right triangle. Here's an example of something that is not an identity, because this is only true for x values of 5. 2 times 5 is 10, minus 3, sure enough, is equal to 7. But what if I plugged in a 6 in there? 2 times 6 is 12, 12 minus 3, that's 9, that's not 7. Therefore, this one is not an identity because it's not true for all possible substitutions of the variables. Okay, so let's look at some of the trig identities. Here's some that we've seen already, some of them have been. So sine and 1 over cosecant, reciprocal ratios, same thing with cos and secant, tan and cotan, and the other ones that we can derive as well. Here's some that you may not have seen already, that anytime I see tangent, I can replace that with sine over cos. Or vice versa, if I see sine cos, I can replace it with tan. Also, cotan should be the reciprocal of this. Sure enough, it is. If I see cos over sine, I can replace it with cotan. Also, one thing that you can do with any identity is you can manipulate it. So for example, this tan equals sine over cos. Tan x equals sine x over cos x. If I wanted to, I could multiply both sides by cos, forming another identity. So tan x times cos x is equal to, if I multiply this side by cos x, they cancel out, and so I'm just left with sine x. So anytime I see tan cos, I can replace that with sine. So that's the idea of what an identity is. Here's some other identities, and these ones are called the Pythagorean identities. If you want to just say Pythagoras's identities, This isn't an English class, so that would be okay. Anyway, here they are. So sine squared plus cos squared is equal to 1. Anytime I see this, I can replace it with a 1. Or anytime I see a 1, I could replace it with that. And likewise, I could replace this with cosecant squared, or 1 plus tan squared. I can replace it with secant squared. Also, manipulations of these. So if I move, say, sine squared to the other side, I come up with a new identity. That is, cos squared x is equal to 1 minus sine squared x. Anytime I see this, I can replace it with that. So that's the game or the magic that's involved with simplifying trig expressions or solving trig equations. That you can look for identities where if I see this, I can replace it with that and see if I can simplify the thing further. So let's do a couple of questions. Here they're asking us to simplify. I take a look and I see 2 brackets and 2 terms within each side brackets. That looks an awful lot like maybe something like this, x minus 3x plus 3. And what did we do with that? We did FOIL. We can do a similar thing with trig. So sine x times sine x is, you could write it as sine x all squared like this. But typically with trig ratios, when we square it like that, typically we write it like this, sine squared x. Sine times cos would be a plus sine x cos x. Minus cos times sine would be a minus, might as well write them in the same order, sine x cos x. And finally, minus cos times cos would be a minus cos squared x. Simplifying now, I have sine x minus sine cos x. These two will cancel, leaving me with sine squared x minus cos squared x. Now I'm wondering at what point I get done these questions, because they seem to be able to go on forever. Typically, one rule of thumb is to try and get them so they have the same trig ratio in them. I see this one has both. I have a sine and a cos. So is there an identity that can help me? I've written one of them up here. Sine squared plus cos squared is equal to 1. So if I wanted to, I could manipulate this identity, maybe push the cos squared to the other side, and so I'd have sine squared x equals 1 minus cos squared x. Anywhere I see a sine squared x, I can replace it with a 1 minus cos squared x. Minus cos squared x. Now simplifying, I have 2 of these, a -1 and another -1, so I have 1 minus 2 cos squared x. This is where I would leave this simplification. So I used FOIL like we've done in lots of times before. I saw 2 terms that were a plus and a minus. They canceled out. Then I looked to see if I had an identity that could replace one of these, trying to get down to 1 trig ratio. You can't always get to 1 trig ratio, but that's sort of a preferred thing. Another preferred thing, just as you're doing some of these, is to use primary ratios as opposed to secondary ones. Let's try some more examples. Oh, looks like I have a distributive property again here. So cosine times secant would be cos y sine y secant y plus cosine times cosecant. So cos y sine y cosecant y. Now I look at these and I say, well, cos and sine, I can't really do much with those, but secant is a reciprocal ratio. I know that secant is the reciprocal of sine. So I can write secant as 1 over sine y. Immediately I see, oh, I could cancel those. So in this term, I would just be left with cos y. Okay, plus, over on this side, let's see what happens. Probably a similar thing can be done with cosecant. That's the same thing as 1 over sine. Oh, I did that wrong, didn't I? That's the same thing as 1 over sine, so these cancel, leaving me with a cos. But did you notice what I did wrong right here? Hopefully you did. I'm just noticing. Secant isn't 1 over sine, it's 1 over cos. Let's go back and fix that. So this is cos y, therefore the cos and this cos will cancel, leaving me with the sine y. Always good to go back and check. Now at this point I do have two trig ratios, but there's nothing really I can do with sine and cos. I could change sine to 1 over cosecant y, and this one could be 1 over secant y, but those aren't a common denominator. I couldn't get those together anyway. And I'm going from primary to secondary or reciprocal ratios, so I probably wouldn't go that far. I'd probably leave it right there. Okay, so there's another example of simplifying trig expressions. Let's try one more, and then we'll go on to some other identities. Okay, cos squared minus 1 all over cos plus 1. In the top here, maybe it might be helpful to write these. Instead of cos theta, I'm just going to call that x squared minus 1. And down here, I'm just going to call that x plus 1. Sometimes it's nice to take and, rather than use the trig ratios, just use the regular x's that we know and love, and then see what we can do. When I see x squared minus 1, I immediately think, oh, that's x minus 1, x plus 1. I can factor that. Well, I can do the same thing with trig ratios. This will be cos theta minus 1 and cos theta plus 1 all over cos theta plus 1. Now you can see that I can cancel this, and the simplification then of that trig expression will simply be cos theta minus 1. So you throwing in x's to try and get what concept or what magic's going to happen is sometimes quite useful for us. Okay, here's some other identities. Oh, these ones look quite nasty. But they tend to be quite useful, especially if I'm looking for the exact value of a particular function or a particular trig ratio. So this one says if I'm taking the sum of two angles and I'm taking the sine of that sum, that what I can do is, rather than do that, I can take the sine of the first times the cos of the second plus the cos of the first times the sine of the second. So anytime I see the sine of the sum of two angles, I could replace it with this long thing. And you might wonder, well, why in the world would you want to do that? Sometimes if I'm looking for the exact value of a function, I have to do this. Similarly, if I'm taking the difference, here's an identity goes along with it. The cosine of the sum, cosine of a difference, tan of a sum, tan of a difference, they all have their identities. On any exam, of course, you'll be given all of these formulas, so you don't need to memorize them. But let's see a couple of examples where we might use these. So first off, the question is asked, what is the cosine of 75? Well, I could just take out my calculator and hit cos 75. Let me do that. Cos 75 equals 0.258. 0.258. But then I'll look back at the question. It says find the exact value. Yeah, well, this is an approximation. I'm going to give you maybe 3 out of 10 on that if I were marking it. I need to find the exact value of this angle. Well, I look at 75 and I say, well, 75 could be expressed as the sum of two angles, 45 and 30. 45 and 30 gives me 75. Now notice that now this is set up as a sum of angles. So I can use this identity that I've written right up here. I can use this identity to help me. So I can say, okay, cos 45 plus 30. So I take the cos of the first one and I multiply it by the cos of the second one. And then I subtract the sine of the first times the sine of the second. Now these are angles that we've memorized before, or we've had, remember those triangles that we memorized, where we had 30 degrees and 60 degrees up here, and then we had things on each side. This was a 1, this was a 2, this was a root 3. And we did the same thing for 45. So if you have those memorized, you can now say, well, cos of 45 is 1 over root 2. Cos of 30 is root 3 over 2. Minus sine of 45 is 1 over root 2. And sine of 30 is 1/2. Now, all that's left to do is to simplify this expression. I need to get a common denominator here. Actually, maybe let's rationalize this denominator. So let's multiply top and bottom by root 2. That'll give me root 2 on the top and 2 on the bottom, times by root 3 over 2. Let's do the same thing with this one. This will be root 2 over 2. Let me just show you that over here. If I have 1 over root 2, I can multiply top and bottom by root 2, leaving me with on the top a root 2, and on the bottom the square root of 4, which is 2. Okay, so that's just rationalizing the denominator. Okay, times 1 over 2. So this root 2 times root 3 is root 6 over 4 minus root 2 over 4. They have a common denominator. I could simplify that by saying root 6 minus root 2 all over 4. That would be my exact value for the cosine of 75 degrees. And I used this sum and difference, or the sum identity of trigonometry, to help me find that exact value. If they didn't use the word exact value, heck, 0.258, 10 out of 10. As soon as they want the exact value, I'm forced to use one of the sum and difference identities. Here's another occasion where using the sum and difference identities is handy. Sometimes you'll be given two ratios, so two angles. I'm looking at angle V and angle U, these two angles, and I'm given two ratios that correspond with those angles. And then the question is, find, in this case, the difference of the sine of those two angles. Well, I don't really know what the angles are. And I'm also looking, I didn't write it in here, but I'm looking for the exact value of the sine of u minus v. So to do that, here's what I do. First off, I would write down my identity. Sine of u minus v is equal to sine u cos v minus cos u sine v. Got it. Now, right from the question, it says that the sine of u is 3 over 5. So sine of u, well, this one here is just 3 over 5. Not the sine of 3 over 5, just 3 over 5. Cos, they don't tell me what that is. Oh, they tell me sine of v is 4 over 5. That's this one over here. So I know the sine of v is 4 over 5. But I don't know what the cos of u, nor do I know what the cos of v are. I need to determine what those are before I can proceed and finish off this calculation. Now, if they've given me the sine ratio of an angle, so if they gave me that the sine of u was equal to 3 over 5, they've actually given me the opposite side and the hypotenuse ratio, the ratio between those two sides. If I know the opposite side and the hypotenuse of angle u, so this is my angle u side, I can determine the adjacent side, which would give me the cosine ratio, right? Adjacent over hypotenuse. So I can come down here and say x squared plus y squared is equal to r squared. So opposite is our y value, so that's 3 squared. And r is our hypotenuse, that's 5 squared. And so right here, I'll be able to determine the x, or the adjacent side. So x squared will be equal to 25 minus 9, or 16. X comes out to being a plus or a minus 4. In the original equation, they said acute angles. So that rules out minus, an x value to be minus. So it has to be positive. So therefore, for angle u, the cosine of u will be whatever the adjacent side, or x side, is over the hypotenuse, or r. So x we've just found out to be 4. We know the hypotenuse is 5. So we now know what the cosine of u is. Cosine of u right there. What was it? 4 over 5. 4 over 5. So now let's determine for angle V what the cosine ratio is. We need to get the cos of V. So let's go to angle V. I know that the sine of V is equal to 4 over 5. So using the same logic, I can go x squared plus y squared is equal to r squared. And you probably have the answer already. Sine is y over r, right? Or opposite over hypotenuse. Notice how I sort of interchange those all the time, and you should be able to do that. So y is 4, so 4 squared is 16, r is 5, that would be 25, x squared plus 16 equals 25. Move the 16 over and subtract. I get x squared is equal to 9, x is equal to a plus or minus 3, because they're both acute, and in that quadrant 1, x must be a positive 3. So therefore, the cos of V will be equal to x over r, or x is 3 and y is 5. So up here then, I got 3/5 for the cos of V. Now to solve this, I'll simply work the equations. 3/5 times 3/5 will give me 9/25, minus 4 times 4, this would be 16/25. So my exact value then will be negative 7 over 25. That will be the exact value of the sine of u minus v. Okay, so again using the sum and difference identity, and also using our understanding of the ratios of a triangle helped us determine that. So in this section we've looked at identities, saw that an identity was something where I could replace any of the variables and it would be true for all of those replacements. And then we looked at a number of the identities to help us both simplify trig expressions and also to simplify or solve for the sum or difference of an angle.